This is the course on fundamentals of transport processes, and this is lecture 7, where we will continue our discussion on diffusion. Welcome. Last class we were discussing the fundamental mechanism of diffusion. As I said, there are two mechanisms of transport, convection and diffusion. Convection is transport due to the mean flow of the fluid, whereas diffusion is the transport due to fluctuations in the molecules. Molecules of both liquids and gases have fluctuating velocities due to thermal noise, and if there were a gradient in temperature, these fluctuations would induce molecules to go from regions where they have a higher concentration to regions where they have a lower concentration. We took the simple example in the last class of the diffusion between two chambers separated by a tube. And in the top chamber we had put in pure molecules of one component, and in the bottom chamber we had a little bit of concentration of a solute mixed in. These red molecules are the solute molecules. And of course, diffusion takes place if we have a stopcock between the two chambers and instantaneously remove it, then all of these molecules are in fluctuating motion. Okay, so, there is no net motion of the center of mass. We are assuming that the concentration of the solute molecules is small enough that the motion of these molecules does not affect the motion of the center of mass. They are all fluctuating, but there are regions where the solute is higher, concentration is higher at the bottom, and region where it is lower. And even though the fluctuating velocities of the molecules have no bias, there will be a net motion of molecules because below the molecules exist and they can travel upwards. Above there are no molecules, there is nothing to travel downwards. Because there is a concentration gradient, there is going to be a transport of molecules. Fundamental mechanism of diffusion. A little more quantitative. Okay, why does diffusion take place? If we have a gradient in the concentration of the solute molecules, then the molecules that are, if you take any particular surface at y, molecules that are going upwards are coming from a distance approximately a mean free path below this surface in a gas. Molecules that are coming downwards are coming from a position approximately one mean free path above. The concentration below is higher, the concentration above is lower. Therefore, the molecules on average will tend to flow upwards if there is a lesser concentration above than below. Obviously, this mechanism works only when there is a concentration gradient. If the concentration were uniform, if there were no variation in the concentration, then the number of molecules going above from below will be exactly equal to the number of molecules going below from above. There will be no net flux, so there is no net transport. Therefore, diffusion is a process driven by a gradient in the concentration, and it is due to the fluctuating velocity of the molecules. We had done this calculation in the last lecture. On average from below, the molecules that go upwards come from a distance of the order of the mean free path below the surface. Mean free path is lambda, and I said that if you actually do the calculation, you will find that they come from a distance of order 2/3 times the mean free path below on average. That means that the flux going upwards is equal to the fluctuating velocity of the molecules times the concentration at the location y minus t 2/3 lambda times the concentration times the velocity of the fluctuations. The actual flux has a numerical factor in front of it, turns out to be 1/4. And then we had to do this important step, which was the Taylor series expansion of the concentration about the location y. This is important. I expanded in a Taylor series in the concentration about the location y, and I retained only the first term in that series expansion. That means I am neglecting all higher terms. Okay. And when I did the expansion and then put that into the expression of the flux, I got a term that was proportional to the gradient in the concentration. Okay. There are higher order terms. The reason we are neglecting them is because the concentration variation has a certain length scale associated with it. If there was a concentration gradient between two plates, that length would be the distance between plates. If there were flux coming out of a spherical particle, that length would be the radius of that particle. It has a length scale associated with that. If that length scale is large compared to the mean free path, then the variation of the concentration with distance dc by dy is approximately proportional to c by that microscopic length scale. Okay, it goes as c divided by that microscopic length scale. Let me just say this. Goes as c divided by that length scale. Okay, and therefore, this term here, okay, this term here, okay, lambda times dc by dy goes as lambda c by L, okay, where L is the macroscopic length scale. There are higher order terms. Okay, I have the next higher order term in this series, which is plus 2 by 3 lambda square by 2 factorial d square c by dy square. Okay. If I look at what this next higher order term is, it is proportional to lambda square d square c by dy square, okay, which is approximately lambda square c by L square. Okay. So, this first term is ordered lambda by c, this next term is ordered lambda square by c square. When the mean free path is small compared to the macroscopic length scale L, then this second term is small compared to this first term. The third term is smaller still, okay, and because of that I can neglect all higher terms. So, diffusion is a phenomenon that can be described by continuum equations only when the macroscopic length scale is large compared to the mean free path or the microscopic scale in the system. We had looked at estimates of these velocities. See, there are the diffusion coefficient that I had got here depends upon two things. Okay. It depends upon the root mean square velocity and the mean free path. Okay. As I said, the diffusion coefficient has dimensions of length square per unit time. Okay. You get that out by writing it as a product of the RMS velocity and the mean free path. Velocity has dimensions of length per time, length is length, and therefore you get length square per time as the diffusion coefficient. So, if I know both lambda as well as VRMS, I can estimate what the diffusion coefficient should be, and that's what we set out to do next. Okay. VRMS from equipartition of energy half mv square is equal to 3 by 2 kT. VRMS is square root of 3 kT by m. Okay. And we estimated that as around 1200 meters per second for hydrogen, about 330 for oxygen, comparable to the speed of sound. Okay. So, you can take the speed of sound approximately as an estimate for the root mean square of the fluctuating velocity of molecules in a gas. Mean free path, we had an argument for that, distance traveled between successive collisions. Okay. As the molecule moves along, it sweeps out a cylinder of diameter pi d square, where d is the diameter of the cylinder. If a second molecule comes within that cylinder, that means there is a collision. Okay. And therefore, if the probability of collision approaches 1, that means that its molecule is inevitably collided. Therefore, the length of the cylinder is equal to the mean free path, and the probability is approximately 1. And from that we got 1 by pi n d square. N is a number density, number of molecules per unit volume, okay, and d is the diameter. Okay. And from that we got the mean free path as approximately 6 into 10 power minus 4 meters per second. Okay. I am sorry, we got the mean free path as approximately 0.5 into 10 power minus 6 for hydrogen and 6 into 10 power minus 8 meters, okay, for oxygen and nitrogen. 6 into 10 power minus 8 is about 60 nanometers, 600 angstroms. Okay. The diameter of these molecules is about 3 to 4 angstroms. Okay. So, there is a large separation between the mean free path and the molecular diameter. Okay. And on this basis, we got the diffusion coefficient as about 10 power minus 5 meter square per second for most gases at standard temperature and pressure. Lighter gases will have a higher diffusion coefficient because their diameter is smaller, they travel longer, their mass is smaller, their fluctuating velocity is larger, therefore, they will have a higher diffusion coefficient. Heavier molecules will have a lower diffusion coefficient. Okay. Next, we looked at fluids, at liquids. Okay. And if you just simplistically estimate the diffusion coefficient of liquids, you would say that that would be about 10 to 100 times smaller than that for gases, because the mean free path in a liquid is approximately comparable to the molecular diameter. In a gas, it varies by about 10 to 100 times the molecular diameter. Because the mean free path is lower, the root mean square velocity is still given by the equipartition argument, and because of that, the root mean square velocities of the molecules at the same temperature in liquids and gases are the same, and therefore, you would simplistically say that the diffusion coefficient is about a 10 to 100 times smaller. Turns out that that is not true. In liquids, for small molecules diffusing in liquids, the diffusion coefficient is actually 10 power minus 9 meter square per second, 4 orders of magnitude smaller than in gases. For large molecules, it is even smaller. It can go all the way from 10 power minus 11 to 10 power minus 13, all in meter square per second. Physical reason for that I had explained in the previous class. A liquid consists of molecules which are very close to each other. So, if one molecule wants to go in any direction, there are other molecules that have to move out of the way. So, the motion of one molecule is not just a function of its velocity and mean free path, but also the collective cooperative motion of all other molecules around it in order to allow it to go in one particular direction. That accounts for the much smaller diffusion coefficient in liquids. So, this is mass diffusion. I should emphasize once again that this is only for tracer mass diffusion, where the concentration of the solute is small, so that there is no real center of mass motion. We will come back to what happens when there is center of mass motion a little later. Okay. So, in the case of gases, as I said, the Vrms is proportional to the square root of the temperature. The mean free path is independent of the square root of temperature. It changes only with the number density of molecules. So, the diffusion coefficient goes as the temperature to the half. Okay. Next, we looked at diffusion of momentum. Fundamental equation, a little bit different. Rate of change of momentum is equal to the sum of the net forces acting on the molecule, acting on the system. So, we took a fluid with a particular cross section across which there was a velocity gradient. Okay. And if we take this differential volume, okay, yeah, just take this, yeah, okay. If we take this volume, okay, then there is an increase in momentum within this volume, because faster moving molecules are coming down, and decrease in momentum because molecules are going upwards. However, there is a mean velocity gradient, okay, which means that on average the molecules that are coming downwards have a higher velocity than the molecules that are going upwards, because the velocity increases as you go upwards in this system. Okay. So, on average there is a net momentum increase of this volume of fluid, okay, because faster moving molecules are coming downwards, slower moving molecules are going upwards. Therefore, there can be a transport of momentum only when there is a gradient in the mean velocity. Okay. And we had used very similar argument to calculate the fluxes. Okay. On average, the molecules that are going upwards, okay, from below to above, they are coming from a distance of the order of a mean free path from below the surface. Okay. That means that the number of molecules going upwards is equal to the root mean square velocity times the density times the velocity at a location approximately 2/3 of a mean free path below the surface. Molecules that are coming downwards from above, Okay. On average, they are coming from a location above the surface. Okay. Therefore, on average, molecules that are coming downwards are coming from a location that is 2/3 of a mean free path above the surface. Okay. And what that means is that the flux downwards is equal to Nm into the velocity at y plus 2/3 lambda times the root mean square velocity with some undetermined constants. Okay. We are only going to estimate the values, so we do not worry too much about the undetermined constants in the problem. Okay. So, we take the difference between what is going upward and what is going downwards, okay, and we ended up with an expression for the stress, okay, as some constant okay, times the root mean square velocity times the mean free path, okay, times Nm. N is the number of molecules per unit volume, m is the mass of a molecule. Therefore, N times m is the density, the number of the mass per unit volume, times du by dy. Okay. So, therefore, the viscosity is approximately root mean square velocity times the mean free path times the number density and the mass of a molecule. Therefore, the shear stress is the viscosity times the velocity gradient. Okay. We could also express this in terms of the momentum density rho times ux, where rho is the mass density, number of molecules into the molecular mass. Okay. And when you express it in that term, you get the shear stress is equal to mu by rho times the gradient of the momentum density. If you recall, when we did the diffusion equation, okay, many lectures ago, I had said that diffusion coefficient, the flux of a quantity, can be expressed as the diffusion coefficient times the gradient of the density of that quantity per unit volume. Flux of mass is equal to mass diffusion coefficient times the gradient in the density of mass or the concentration. Flux of momentum diffusion coefficient times the gradient of the momentum density. So, here we have the gradient of the momentum density, okay, and sitting in front is the momentum diffusion coefficient, which is just equal to the kinematic viscosity mu by rho. Okay. And it also has dimensions of length square per unit time, and it is proportional to Vrms times lambda. So, therefore, the momentum transport and the mass transport in gases have the exact same mechanism. Okay. So, in this case, for example, the viscosity is proportional to the mass density times the momentum diffusivity. Okay. You can do more sophisticated calculations and actually find out what those constants are using kinetic theory of gases. Okay. For monatomic molecules, okay, in the very dilute regime, turns out that those constants give you are 5 by 16 d square mkt by pi power half. Okay. So, therefore, the kinematic viscosity will be equal to mu by n times m, okay, which will be equal to 5 by 16 n d square, okay, into kt by m into pi power half. Okay. So, that is the kinematic viscosity. Okay. Recall the formula for the diffusion coefficient. The mass diffusion coefficient that I had got was 3 by 8 m d square kt by pi m power half. Okay. So, straight away from this I can get the Schmidt number, which is the ratio of the kinematic viscosity and the mass diffusivity, or the ratio of momentum and mass diffusivity. Okay. Schmidt number is equal to nu by d, okay, which is equal to 5 by 6 for dilute monatomic gases. Okay. So, because the mechanism of mass and momentum transfer in gases are the same, both require the physical transport of molecules across a surface. Therefore, the diffusivities that you get will also be the same. Okay. Now, how about momentum transport in liquids? So, when we discussed mass transport, okay, I had said that naively you would expect that the mass diffusivity for liquids is about 10 to 100 times smaller than that in gases, simply because the mean free path is smaller, the fluctuating velocity is approximately the same. Turns out not to be so. Turns out that for the physical motion of molecules, you require all molecules around it to also move, because the transport of solute molecules requires that particular molecule to diffuse through the fluid. Okay. So, that requires a physical motion of one particular molecule. Okay. Momentum transfer does not require the physical motion of a molecule. Okay. So, if I have some surface and I have a liquid in which the molecules are separated by distances comparable to the mean free path, okay, and I apply a velocity gradient across. Okay. For momentum to get transferred in any one direction, okay, it is not necessary that one particular molecule actually move in that direction, because this molecule can transmit momentum to the adjoining molecule. Okay, and in that way there can be momentum transfer. After all, momentum can be transferred not just by the motion of a faster molecule across the surface, but also because the faster molecule interacts with the molecule next to it and transfers some momentum. Okay. So, the transfer of momentum does not physically require the transport of a molecule. Okay. And due to this, momentum transfer in liquids is much higher than mass transfer in liquids. Okay. The Schmidt number for liquids is typically large. Okay. The kinematic viscosity for water is approximately 10 power minus 6 meter square per second. Okay. The kinematic viscosity for air is approximately 1.5 into 10 power minus 5 meter square per second. Okay. And there is not that much difference. Okay. I told you that the kinematic viscosity and the mass diffusivity for gases are all of the same magnitude, all approximately 10 power minus 5 meter square per second. However, the kinematic viscosity of liquids is actually much larger than the mass diffusivity of liquids. The reason is because for momentum to be transported, you do not need the physical transport of molecules across a surface. It is sufficient if forces are exerted by interacting molecules across that surface. Okay. Therefore, momentum diffusion is a much faster process, and actually the Schmidt number in liquids, okay, which is nu by d, could be as high as 1000. Okay. So, momentum diffusion in liquids is typically much faster than mass diffusion in liquids. Okay. Now, so that is as far as mass and momentum diffusion are concerned. Let us go on to the third topic, okay, that is energy diffusion. Okay. Energy diffusion obviously takes place due to gradients in temperature. Okay. So, the physical mechanism for gases at least, okay, is the same as the physical mechanism for mass and momentum diffusion. Okay. Let us say I had a surface with molecules all around, okay, of a gas, each having its own fluctuating velocity. And there was a temperature gradient across as a function of this coordinate y. Okay, so just okay, there's a gradient in the temperature. Temperature is higher above and lower below. Okay. That is going to result in a transport of energy. Okay. Mechanism is very simple. Because the temperature is higher above, molecules that are coming down from above have an average, on average, a higher energy. Temperature is lower below, so molecules that are going from below to above, on average, have a higher, lower energy. This is going to result in a net flux of energy across the surface. Okay. Okay. So let us once again calculate the fluxes. Okay. The flux of energy, okay, going upwards. Okay. Okay, the flux of energy going upwards, okay, from below the surface is going to be equal to the energy below the surface. Okay. The energy at a location below the surface. Okay. If we assume that the system is a gas at constant volume, then the specific energy, okay, let us just work with the specific energy. Okay, so this is going to be equal to the energy at y minus 2 by 3 lambda. Okay. This is the specific energy, the energy density, okay, at a distance y minus 2 lambda, okay, into the RMS velocity, okay, RMS velocity across the surface. Okay. The flux of energy that is going downwards from above, okay, times some constant, which I said was approximately 1 by 4. Okay. The flux of energy going below, okay, comes from a distance of the order of lambda above the surface. Okay. So, this will be 1 by 4 E into y plus 2 by 3 lambda into Vrms. Okay. So, the net flux is equal to the flux going above minus the flux going below. Okay. So, the net flux J is equal to J plus minus J minus. Okay. The net flux is equal to the flux going above minus the flux going below. Okay. So, this is equal to 1 by 4th Vrms into E at y minus 2 by 3 lambda minus E at y plus 2/3 lambda. Okay. And I use a Taylor series expansion once again. Okay, I use a Taylor series expansion once again for this. Okay. So, this is equal to 1 by 4 Vrms into E at y minus 2 by 3 lambda dE by dy, okay, at the location y, minus E at the location y minus 2 by 3 dE by dy at the location y times lambda. Okay. And if you put all of this together, you will get approximately 1 by 3 Vrms lambda times dE by dy, okay, where E is the specific energy, energy per unit volume. Okay. So, this now is the thermal diffusion coefficient, exactly the same in form as the mass diffusion and the momentum diffusion coefficient. But this is the net flux. Okay. This is the net flux of heat. Okay. The equation that we are usually used to is of the form the heat flux is equal to minus k into dt by dy. Okay. That is Fourier's law for heat conduction. So, in order to get this equation into this form, we have to write the energy flux as 1/3 lambda Vrms into d by dy of the energy density, energy per unit volume. If the system is at constant volume, okay, then this will be the mass density times specific volume into temperature. Okay. Mass density, as I told you, is equal to number density times molecular mass, okay, with the negative sign here. Okay. So, this is approximately equal to minus 1 by 3 lambda Vrms rho Cv dt by dy. And this whole thing is the thermal conductivity K. Okay. So, in kinetic theory of gases, the thermal conductivity is equal to lambda Vrms into the density. Density is number density times the mass times the specific volume. Okay. So, that is the expression for the thermal conductivity. Okay. I said the mean free path was going as n d square. Okay. Vrms is square root of 3 kT by m, then I have n m and then Cv. Okay. For a gas at constant volume, Cv is equal to 3 by 2 K. Okay. For a gas at constant volume, Cv is equal to 3 by 2 K. Okay. And of course, there is an undetermined constant here, okay, because this is approximately equal to, I have had factors of order 1 which I have suppressed in this calculation. Okay. So, I can only get it up to an unknown constant. Okay. In kinetic theory of gases, you can do a more exact calculation. Once again, for a monatomic gas with only translational degrees of freedom, the expression that you will get for the thermal conductivity is K is equal to 75 by 64 T square into K cubed T by pi m or half. It's not half. Okay, so that is a more exact expression you will get. This is also equal to 5 by 2 Cv times the expression for the viscosity. Okay. The two turn out to be exact, because in the expression for Cv I had 5 by 16 root pi. Okay. If I multiply that by 5 by 2 and Cv is 3 halves of monatomic gas, I will get 75 by 64 root pi T square. Okay. So, this is an exact expression for the thermal conductivity of monatomic gas of spherical molecules. Okay. I can calculate, in the previous case when I did mass diffusion, I calculated for you the Schmidt number. I can now calculate for you the Prandtl number using this expression. Okay. The Prandtl number is equal to K by rho Cp. Okay, the Prandtl number is equal to K by rho Cp. Okay. And I am sorry, the Prandtl number is equal to Cp mu by K, okay, which is equal to 2 by 5 Cp by Cv. Okay. And Cp by Cv for a monatomic gas, 3 degrees of freedom, Cv is 3 by 2 K, Cp is 5 by 2 K. The ratio gamma, ratio of specific heats, is 5 by 3. Okay. So, this Prandtl number turns out to be 2 by 3 for a gas of monatomic molecules. Order 1, okay, it is approximately equal to 1. The ratio of the momentum and thermal diffusivities are both approximately of order 1. Okay. The reason is because both of these take place by the same mechanism, the physical transport of molecules. For monatomic gases, the number is approximately 2 by 3. For larger molecules, the number goes closer to, okay, for larger molecules, Prandtl number goes to 1. Okay. That is because the ratio of specific heats is approximately 1 for large molecules. Okay. So, this gives us a prediction for what the Prandtl number should be for gases. Okay. The mechanism of transport is exactly the same. For transporting mass, for transporting momentum, and for transporting energy in gases, you require physical motion of molecules. The reason is because the distance between molecules is large compared to the molecular size. So, molecules cannot effectively transport momentum and energy just by interactions, by long distance interactions, because the distance between molecules is very long. Therefore, it is essential that molecules are transported in order for both for all three, mass, momentum and energy diffusion, to take place. And because you require the physical motion of molecules, the diffusivities that you get are all approximately of the same magnitude. Okay. For example, the diffusivity alpha for thermal conductivity is going to be equal to K by rho Cp. Okay. And rho was equal to and K was equal to lambda Vrms times rho Cv. So, you will get approximately Cv by Cp times lambda Vrms. Okay. This is a dimensionless number, okay, and this thing is the same diffusion coefficient we had earlier for both mass and momentum diffusivity, mean free path times the fluctuating velocity. Okay. And it is because of this that for gases the transport mechanisms are the same for both mass, momentum and energy, and the diffusivities are also approximately the same. The Schmidt number was 5 by 6, the Prandtl number is 2 by 3 for monatomic gases. In the case of mass diffusion, we saw that the mass diffusivity is much smaller than the momentum diffusivity in liquids, because mass diffusion requires the physical transport of a solute molecule. Momentum diffusion does not. It can take place due to interactions between molecules. How about thermal diffusion in liquids? Okay. In liquids, thermal diffusion can take place due to different mechanisms depending upon the nature of the liquid. Okay. For example, for liquid metals, okay, you do not require the physical motion of molecules for energy conduction, for temperature, for the transport of heat. Okay. You do not even require the molecules to transmit heat from one molecule to the other. Okay. The molecules in liquids, they have electron clouds all around them. Okay. And these electron clouds can result in very fast, the electron clouds is essentially shared by all the molecules, and this can result in very fast thermal conduction. Okay. Therefore, the thermal conductivities of liquid metals are very high, because the mechanism of transport is basically due to the transport due to the electron clouds, which is shared by all the molecules. Okay. Due to that, the Prandtl number, which is the ratio of momentum diffusion by thermal diffusion, is actually much smaller than 1. Okay. For example, for liquid mercury, Prandtl number is about 0.015. Okay. That means that thermal diffusion is 60 times faster than momentum diffusion. And as I told you, momentum diffusion in liquids is faster still than mass diffusion. Okay. So, because of this very efficient method of transport, the Prandtl number for liquids is actually very small. Okay. In contrast, if you had large organic molecules, okay, they do not transfer energy very quickly. Okay. The momentum diffusion in the case of large organic molecules, okay, the Prandtl number can vary anywhere from 10 power minus 4 to 10 power minus 2. Okay. It is very small. Okay. And therefore, the momentum diffusion is actually much faster than the thermal diffusion. Okay. Water, for example, is somewhere in between. Prandtl number is about 7, okay, for water. Okay. So, it is somewhere in between these different cases. Okay. So, in thermal conduction, it is a different process. The reason is because the mechanisms can be very different. Okay. In some cases, like in liquid metals, transport is very fast because it takes place due to the electron clouds around the molecules. In other cases, thermal conduction is very slow. Prandtl number actually has a very large range. Okay. It goes all the way from 10 power minus 4 to I am sorry, this should be 10 power plus 4. 10 power 2 to 10 power 4. Okay. Okay, so, it could be as large as 10 power 4, it could be as small as 10 power minus 2, and normal liquids fall somewhere in between. Liquid metals are special cases, and very insulating liquids are the opposite special case. Okay. So, this is a brief discussion of diffusion phenomena. Before I leave, there's I promised that I'd discuss the difference between diffusion in the case of dilute solutions and normal multi-component diffusion. Okay. So, let me just briefly deal with that. Okay. as I said, diffusion is transport which does not require the motion of the center of mass. Okay. So, in that case, for example, when I had two bulbs, okay, separated, okay, by some distance with a stopcock in between, okay, and I had molecules, okay, and a few tracer molecules on one side, right. Since all of the black molecules are all identical to each other, the motion of the tracer molecules did not affect the motion of the center of mass very much. Okay. On the other hand, if I have diffusion between two very different molecules, okay, let us say I had oxygen on one side and much smaller hydrogen on the other side. Okay. The molecular mass of hydrogen is only 2, whereas oxygen is 32. So, initially the mass on the left side would have been higher than the mass on the right side. Okay. But as diffusion progresses, heavier molecules are going to the right and lighter molecules are coming to the left, due to which the center of gravity of the system is actually going to the right. Okay. So, that represents the motion of the center of mass. Okay. Therefore, there is, in addition to diffusion in this system, there is also convection, there is also motion of center of mass. Okay. Now, how do you account for that? You have to write the fluxes a little differently. Okay. I write the flux of one component, okay. Let us say this is component 1 and this is component 2. Okay. I write the flux of one component as the diffusion flux, okay, plus the concentration times the velocity of the center of mass. Okay. And I write the flux of the second component as the diffusion flux plus the velocity of the center of mass. Okay. Now, how do you calculate the velocity of the center of mass? From the total transfer. Okay. So, N1 plus N2 is the total flux, total mass flux. Okay. This one has got to be equal to C1 plus C2 times the velocity of center of mass. Okay. So, from this I can calculate what is the velocity of the center of mass and then put that in here to calculate what is the total flux. Once you have done that, the diffusion flux alone, okay, J1 is equal to minus d dC1 by dy. Okay. So, in addition to the motion of the center of mass, there is actually a flux relative to the center of mass. In multi-component systems, both of these are simultaneously present and we have to account for both of them. Okay. And finally, a little bit of variety in this diffusion process. Can there be diffusion of mass due to temperature gradient? Can there be diffusion of energy due to gradient in the density? Okay. It turns out a temperature gradient can in fact give you a diffusion of energy, a diffusion of mass. Okay. And the reason is as follows. Okay. When we had earlier done the problem of the diffusion of mass, okay, the molecules which had fluctuating motion. I said that the flux going upwards, okay, was equal to some constant, in that case I got 1/4, times the fluctuating velocity times the concentration at a location y minus 2 by 3 lambda. Okay. Now, if there were no concentration gradient, but there were a temperature gradient, okay, if there were temperature gradient, okay, with the coordinate y, then for the flux going upwards, I would have to take the RMS velocity at that location y minus 2 by 3 lambda. Okay. So, what I need to write is that this is equal to Vrms times at y minus 2 by 3 lambda into concentration at y minus 2 by 3 lambda. Okay. No concentration gradient. Okay. Therefore, this is equal to 1 by 4th Vrms at y minus 2 by 3 lambda into the concentration at y itself, because there is no concentration gradient. Flux going downwards will be 1 by 4th. The RMS velocity is at some location above the plane times the concentration at y, because there is no concentration gradient, but there is a temperature gradient, and therefore, the fluctuating velocity of the molecules is different. Okay. Add these two together, okay, J plus minus J minus is equal to 1 by 4th C into Vrms at y minus 2 by 3 lambda minus Vrms at y plus 2 by 3 lambda. Okay. So, this, after doing all the manipulations that we have done for the previous cases, this will give me 1 by 3 C times dVRMS by dy. Okay. The RMS velocity is square root of 3 kT by m. So, you get 1 by 3 C d by dy of square root of 3 kT by m. Okay. And therefore, I can do the differentiation to get 1 by 3 C into square root of 3 kT by m into 1 by 2 t dt by dy. Okay. When I differentiate t power half, I get 1 over t times dt by dy. So, if I have a temperature gradient, I can generate a mass flux. Okay. There can be a mass flux due to a temperature gradient. Okay. In a similar manner, can there be an energy flux due to a gradient in the concentration, okay, or a gradient in the density? Okay. Of course, there can be an energy flux, because if there is a gradient in density, there is on average molecules going upwards. They are carrying their energy with them, okay, and therefore, there is going to be an energy transport due to the fact that the molecules, which are on average traveling upwards, the center of mass is traveling upwards, that is going to give you an energy transport as well. Can there be momentum transfer? No, because momentum is actually a vector. Because of that, there cannot be momentum transfer unless molecules on average have a bias towards motion in one direction or the other. Okay. So, because of that, there can be temperature, there can be mass transfer due to temperature gradients, there can be energy transfer due to density gradients. These are concentration gradients. These are called reciprocal relations, which relate fluxes of one quantity to gradients of the other quantity. They are possible, okay, and there are actually reciprocal relations that relate the constants in those equations. Okay. However, in the present course, we will not go into that discussion. We will not consider energy transport due to concentration gradients or mass transport due to energy gradients. We will restrict attention to these equations for motion. Okay. So, we now come to the end of our discussion on diffusion. Okay. And next class we will go on to the actual core of the present course, which is to actually discuss how does one solve equations for the transport of materials. Okay. So, that starts in the next lecture, lecture number 8. Before we go there, this basically completes the introduction part of this course. I first told you that what we are trying to do in this course is actually solve for the fluxes that are generated due to gradients in certain quantities. Okay. The quantities that are of interest to us are mass, momentum and energy. These are important in physical situations. For example, if you have a catalyst particle, it's not just if you have a heterogeneous catalyst reaction happening in some reactor, it's not enough to sufficient to just put in the reactants in and take the products out. One is also to make sure that the reactants actually get to the surface where the reaction occurs. The products get out of that surface. Heat is transferred as necessary. If it's endothermic, heat has to be transferred to the reaction location. If it's exothermic, heat has to be transferred out of that reaction location. So, we are looking in detail at what happens at places where transport actually takes place. In heat exchangers, for example, it is not sufficient to just ensure that there is hot fluid coming in, cold fluid going out. You also have to ensure that transport is taking place across the surface. Okay. So, we are focusing on those areas which are most crucial for these transport processes to occur. Okay. Before going there, I first took you through the fundamentals of dimensional analysis with the objective of giving a physical interpretation to the dimensionless numbers that we have been using all along. Okay. One class of dimensionless numbers are the dimensionless fluxes. Okay. I discussed those, the Nusselt number, the drag coefficients, the friction factor, and those are functions of other dimensionless groups, broadly classified as either the ratio of convection and diffusion or the ratio of two diffusivities. Okay. Ratio of convection and diffusion, Reynolds number for momentum transfer, and a Speckley number for both heat and mass transfer. Okay. Ratio of two diffusivities, Schmidt number, ratio of momentum and mass diffusion, the Prandtl number, ratio of momentum and thermal diffusion. Okay. And so, ultimately if you do the balance around the entire volume, you will get average dimensionless fluxes, the dimensionless heat flux, the dimensionless mass flux, and the drag coefficients of the friction factor for momentum as a function of these dimensionless numbers. Okay. But those were written for the entire system. The dimensionless heat flux was written as was scaled by the average difference in temperature between the wall and the fluid. Dimensionless mass fluxes were written as the average difference in concentration between the reactor surface and far away. Okay. And these were written in terms of scaled velocities, okay, in the system. And our objective was to go closer and look at what happens very close to surfaces. And we wanted to write down equations which told us how these quantities vary throughout the domain, not just between the surface and far away, but rather throughout the entire domain. Okay. And before we went there, I said we should look at diffusion. Okay. Take a look at what are the mechanisms of diffusion and why do diffusion coefficients have the kinds of numbers that they actually do. Okay. So, for example, in these lectures on diffusion coefficient, in gases the diffusion process occurs by the same physical mechanism for both mass, momentum and energy transport. Okay. And because of that, all diffusion coefficients end up being approximately given by the root mean square velocity times the mean free path in all three cases. Okay. I just told you that the Prandtl number is 2 by 3, the Schmidt number is 5 by 6 for monatomic gases of hard particles. Okay. In liquids, these transport processes occur due to different mechanisms. Okay. In the case of liquid metals, there is very fast thermal conduction, but momentum transport is not as fast. Okay. Mass diffusion in liquids is typically much slower than either momentum or thermal diffusion. Mass diffusion is much slower because for a solute molecule to diffuse through a liquid, it is necessary that the surrounding molecules move out of the way. So, one molecule, the motion of one molecule does not require the motion of that molecule alone, but the cooperative motion of a larger region, so that all other molecules move out of the way, okay, and this molecule can diffuse through. For that reason, mass diffusion is a very slow process in the case of liquids. Momentum diffusion does not require the motion of molecules physically. It can take place due to the forces exerted by one molecule or another. Okay. So, therefore, momentum diffusion is faster. Thermal diffusion it depends upon the mechanism by which thermal diffusion takes place. In liquid metals, it is very fast because of the transfer of energy due to the electron clouds around the molecules. In the case of organic molecules, it is very slow. There is a whole range. Okay. So, this completes our introduction to why we need fundamentals of transport processes. Okay, that was the first question that I asked in the very first lecture. What is it that we are going to do? We are going to look at whether we can get in simple systems around a single catalyst particle in a single tube, cylindrical tube, okay, near a flat surface. Can we get the entire variation of the concentration, temperature, velocity fields, okay, not just the differences in the average values, okay, for simple situations, not for complicated situations like heat exchangers and so on, for simple situations. If we can get that, we can exactly calculate, okay, why the dimensionless fluxes that have the form that they do in specific situations. Okay. So, we will start off on unidirectional transport in the next class, where we will see transport only in one direction. Okay. Simplest situation is actually the transport between, let us say, two flat plates. You have a liquid between two flat plates, you heat one, the other is cool. How much energy goes through between the two? Okay. That is a simple example, because we know that the temperature gradient is linear and the heat flux we can get quite easily. However, you can have more complicated situations where it is not steady. Okay. In those cases, how do we solve these problems? We will see in the next class. So, we will start unidirectional transport in the next lecture. See you then.